Well, it turns out that in order to learn more about galaxies, or actually the rest of the universe, more than just the shapes or colors or the types of the galaxies, we need to know how far away they are. And measuring distances to galaxies turns out to be actually one of the most challenging tasks we face when trying to understand galaxies and the universe as a whole. But the payoff is enormous. These measurements not only tell us the galactic distances, but also reveal the real sizes and ages of those things that happen inside the galaxies, and moreover, the size and age of the observable universe. So, how do we measure distances? Remember when we had discussed about just stars, just any object out there, right? Let's compare these two. Obviously, this seems to be or appears luminous, more luminous than this one. This one appears fainter. But the question is this faint star far away or intrinsically not very luminous? And then this one, is it bright because it is nearby, or is it bright because it is intrinsically very luminous, right? So brightness alone, or brightness, is how they appear to us, right? That is at surface of the Earth, does not actually provide enough information to measure distances. Right? So remember, if this is a star, and that means it's going to emit in all directions, but it's going to depend a lot, right? How luminous we see it, it's going to depend on how far away we are, right? So that's going to be the distance. And remember, brightness is actually intrinsic luminosity divided by this whole area, surface area of a sphere is 4 pi radius square, and the radius distance is the radius of sphere, right? All that light that is produced by the star is going to be dissipated on the surface of a sphere. So it's going to be 4 pi, the brightness is going to be the luminosity divided by 4 pi distance squared. Okay? So, our determinations of astronomical distances definitely depend, and as we will see, on a chain of methods. Okay, in which we develop, in which each step in that chain allows us to measure greater and greater distances in the universe, right? Chain of methods from nearby, and this is step 1, measuring distances, for example, within our solar system, and we do that using radar measurements to further and further away. But outside the solar system, distances become too large for us to wait for that radar system to basically go there and then wait for it to come back. It's going to take too long, okay, for that signal to travel. Step number 2, that involves getting to measure distances to some of the most nearby stars, okay? They're too far away, okay? So these nearby stars, they're too far away for radar ranging. However, we do have another method, and that is, and we discussed that already, the parallax, right? So all we measure is the shift as the Earth moves around the sun, okay? So as long as we know this distance between the Earth and the sun, and that is through radar measurements or radar ranging, right? And it is important. Then we can measure this angle, and then through some trigonometry, actually simple trigonometry, we're not going to go into that, we get the distance between the Earth and that nearby star. All right, but that only works for the nearby stars, right? So far away stars have too small of parallaxes. Too small, basically unmeasurable. And so what do we do then? It turns out we are going to have to rely on the so-called standard candles. We need to be able to find objects whose luminosity we can determine, or we know, or we can estimate without measuring its distance. Because then, knowing this relationship between the apparent brightness and the intrinsic total power output, just a reminder of what we mean by luminosity, and this is not correct, this is going to be distance squared, right? Once we know that, so now if we know the luminosity and the apparent brightness, we can solve for distance, okay? And from that formula, that is going to be luminosity divided by 4 pi times brightness, but that would have been distance squared, right? And so distance is going to be square root of that thing, luminosity 4 pi times brightness, right? So all we need to know now is that intrinsic brightness for a standard candle. And then we measure with our telescopes the apparent brightness, or just how bright that object, that star, looks like at the surface of the Earth. Do we know any candles? It turns out one of the best standard candles is the main sequence of any star clusters. Remember that HR diagram? Remember how we have here the luminosity, but it can also be the relative apparent brightness. And then we have here the surface temperature that increases this way. So maybe for one nearby cluster, we can use parallax and we can get the distance. So maybe that would be this one, known distance. And then we can compare the relative apparent brightness of this cluster of stars with a new one. This would be further away. And what we find is the difference or the ratio in the brightness, right? But the thing is, the luminosity needs to be the same, because those main sequences, right, they are identical in all clusters. More or less identical, but very much the same, okay? And so the luminosities, the intrinsic luminosities of these stars are the same. So the only difference basically is given by the distance. So we're not going to go into the formula that goes into finding that, but it's basically a comparison of the location of the main sequence on the HR diagram. And boom, we get the cluster, a new cluster's distance, because we know by comparison where another cluster for which you know the distance is, and that number, right, is basically, if that is, say, the ratio, so the brightness of this star in the Hyades cluster is 7.5 times higher than the same kind of star, the type of star in the Pleiades, then the luminosity of the distance of the Hyades is going to be square root of 7.5 times the distance of the Pleiades. And that's it. And it's pretty neat, right? We don't need to measure every single star, and we cannot measure parallaxes, right, in that Hyades. So far away that, right, we cannot measure parallaxes in that cluster. And so the only way is, and actually this method has a name, it's called main sequence fitting method. Okay. But of course, we're not going to be able to identify every single little star in clusters of stars in other galaxies. So in order to actually move to further distances, we need to find different kinds of standard candles. And those are a special type of star that live in the so-called instability strip. There are some special kind of giant stars that are very luminous, and they have some special properties. They are summarized here, and we're going to talk about them in a second. And we get to see, because these things are very luminous, we move to further distances. We can actually observe these Cepheids variables. They're so luminous, they can be observed in other galaxies. In other galaxies where we cannot separate or resolve main sequence stars to proceed with the main sequence fitting that we just talked about. So here's what happens. So for the Cepheid variables, so we have the apparent brightness, okay, as a function of time. And they, what do? They are getting dimmer and brighter, and we can actually measure how long it takes for this variability. And so they are variable, right? They're brighter and then dimmer, and we can measure, the time it takes from peak to peak, and that would be the period. We can measure that period, and it turns out there was a very smart woman astronomer who realized that the average luminosity, so it's going to be an average luminosity, and that's plotted here for a bunch of Cepheids, that correlates with their periods. Okay? So it looks like this. So it was actually Henrietta Livid in 1912. She discovered that for the Cepheid variable stars, the longer their periods are, right? So kind of like this in their variability. So we have brightness, and then time, right? So longer, then they are more luminous. So basically they look like this, right? So period, these are longer periods, and these are shorter. And you see the shorter ones, they are less luminous. So what does this mean? This is an amazing finding, okay? That means all we need to measure is the period. We don't need to know intrinsically how bright they are. All we need to measure, all we need to do is monitor the brightness of those stars, okay? And then say, we find the period, and then we go, here's the period, maybe it is something like, 15 days. And then we go to this relationship and say, okay, well, the average luminosity of that star must be somewhere around here. So we basically use that relation between the period and the luminosity, and we find the luminosity, right? We had already, so it was brightness is a function of time, right? So it was like this. We measure the period, but we can also measure the average brightness. And once we have the average brightness and the luminosity, then we use the inverse square law, and we get the distance. Remember that formula? It was luminosity, square root of luminosity divided by 4 pi times average brightness. And boom, then we get to know the distance to that galaxy that was hosting that type of Cepheid variable. So that was amazing, and now we could actually find distances to really far away galaxies. Turns out that it was actually thanks to the Cepheids and Henrietta Livid's discovery of that relationship that Hubble, Sir Edwin Hubble, was able to measure for the first time distances to other galaxies, and that happened in 1923. Just before that, people didn't know, right? So what was it? Just 100 years, like less than 100 years ago, right? We didn't know what the galaxies are. We didn't know whether those spiral nebulae are things that are inside our own galaxy or outside. And so it was actually thanks to using Cepheids as standard candles that allowed Sir Edwin Hubble, the astronomer Hubble, to measure those distances and realize they are much further away than we thought, okay? And it's not just 106 times light years away. That would definitely be like within our own galaxy. It's 10 to the 6, so million light years away, right? This Andromeda, which is the closest large galaxy to Milky Way, and that is a few millions of light years away from us. Okay, so definitely not inside the Milky Way. But there are things that are further away. So it turns out to go even further to galaxies where individual stars, even the Cepheids, are probably not bright enough to be seen. We needed to find some even more powerful standard candles, and those are the white dwarf supernovae. Remember, we talked about the endpoints of stars of various masses, and we had the supernova that was the result of a core collapse of a very massive star, and then it was the white dwarf supernova that was the result of a limit in the mass that can be accumulated on the surface or on a white dwarf. And they are very luminous. Actually, some of the most luminous things in the universe, and they obviously, because they're luminous, they can be seen really far away. So the word here was up to 10 billion. Now we are into the billions, so we have 10 to the 9 light years, right? These are really, really far away objects. We're getting maybe to the edge of the universe. I don't know. We're gonna have to find out, right? But in order to find the edge of the universe, we really need to be able to measure all those distances. So in homework, you're gonna meet with examples like this. This is the light curve of a white dwarf supernova, right? So starts from 0, the apparent brightness, and it's suddenly bright. So this would be the one, just something that appears, that nova, but it's actually supernova because it's much, much more luminous than a nova. So its brightness rises to really high levels of luminosity, and then it fades away, because this is time. And here are some examples of how the galaxies look like before the supernova explosions and after. And you can definitely see them in these pictures. And here is another example of a white dwarf supernova that's near its, the peak brightness. So yeah, they exist and they are very, very useful. So again, why are they standard candles? Because they happen thanks to a well-defined limit in a mass of matter, and that is mostly hydrogen, that can be basically dumped on a white dwarf. Remember maybe that white dwarf limit? It was 1.4 solar masses, right? There are no white dwarfs that are more massive than 1.4 times the mass of the sun. And that limit, so this is mass, my handwriting, that actually can be converted into a certain luminosity limit, okay? So this is well known, can be calculated. Okay, so the total amount of radiation that is produced by that limit actually can be calculated, and once we know that limit, then compare with brightness and get distances. All right, it turns out that at about the same billions of light years away, so very large distances, so we're going to call that step, not step 6, but it's, it's at about the same distances, we can actually use entire galaxies as standard candles, because two astronomers, Tully and Fisher, figured out that the luminosity of a galaxy actually correlates with the rotation speed of that galaxy. How do we measure the rotation speeds? Well, so you have parts of the galaxies, the whole galaxy is rotating, parts of galaxies are moving away from us, and parts of the galaxies are moving away from us, and so it's red shifted, and then there are parts of the galaxies that are moving towards us. And so Doppler measurements can give us the rotational velocity. And once we have that, right, and we don't need, right, with no need to know how luminous is the galaxy, then you go here, measure the rotation speed again from Doppler measurements, and then you go to this relation, and it looks like that particular rotational speed is going to correspond to a certain luminosity. Once we know the luminosity, again, compare with brightness and find the distance, which is pretty neat. So we do measure distances to galaxies, distances to further and further away things. So this would be distance increasing this way. This is us on the surface of the Earth. So again, for things within the solar systems, we use this solar system, right? Only one, we use radar ranging. And then for nearby stars, we use the parallax. And then we use the parallax to find the luminosity of nearby clusters. And then we compare the main sequence. And we fit the main sequence and then we compare. Okay? And that comparison is giving us the distance to the further away cluster for which we were not able to measure the distances by calculating parallaxes, those things being too far away, parallaxes being too small for our instruments to actually be able to measure those. And then even further away, we need those really luminous, the variable stars, for which we measure the period, and then we go to this Livid relation. This is not a good color. There you go. So this is what we measure. And then through that relation, we get to know the luminosity. So again, once we know the intrinsic power output, which is the luminosity, then we can compare with the brightness, the apparent brightness, what we measure on the surface of the Earth, and that's going to give us the distance. And then for even more distant galaxies, we have more distant standards, and we have two of them, the white dwarf supernovae, or the type 1a supernovae, or the Tully-Fisher relation, which relates the rotational velocity of a galaxy with its whole luminosity, right? So again, very useful methods and ingenious if you want. And that's how we kind of get to, basically, that's how we got to really, really far away objects. Now, for the rest of the universe, we use so-called Hubble's law, about which we're going to learn next.